see that in your, by the way, I get to see your attendance in this online, what is that called, SAM. And you know that there is attendance criteria. Okay. And if this is the case, if people are somehow not willing to come from one building apart, I don't see the point of coming like 30 kilometers apart, right? I can take the class online there also. Okay. So what we'll do today, we'll do some examples of all the formulas that we learned. And those, basically we learned one strategy and applied it to context, and they boil down to the same thing, basically the same thing. And even though the derivation and all this looks lengthy, but their actual problems are very easy to solve. Right? So these are the problems we'll solve. So let's solve examples which are typical to a generic UG syllabus. So one is, of course, various variants of particle in a box. 1D problems, basically. 1D, you know there is no degeneracy. You proved that theorem. So harmonic oscillator. So degeneracy is possible only in 2D and higher dimension. So then the third class is a 2D version of this. And the so this is the third part is actually we will do in some details. So what I'll do, I'll give a outline solution of this class of problem, because there is a wide variety of problems you can do under this category. This one I'll show you in a little more detail, and these things I will also show this one, actually 2D and 3D. So this one I'll show in somewhat details. And I will also show one more problem for degenerate perturbation theory in somewhat more detail. And central force, then I will spend one whole day. I hope today I will go up to this, cover up to this. I will not solve all the problems in detail, some of them. And all, it's useful that you go through the actual solution. They are very easy, worked out in any textbook. There's not much point in somebody telling and you are listening. It's better to solve it yourself. So central force I will discuss in somewhat a little more detail, because this problem played an important role in the development of quantum mechanics, and especially in the context of experiments, because these where the central force is basically hydrogen atom, and quantum mechanics was discovered through spectroscopy, mainly spectroscopy, where basically people were putting gas of particular certain atoms or molecules, and in a chamber, and putting a strong electric field or magnetic field in that gas, and looking at their spectroscopy signal. Basically, that was the whole story of whole set of experiments which led to quantum mechanics. And there was all these mysteries that even when people formulated quantum mechanics, it was clear, okay, people are getting the fact that there are discrete energy levels, which is the first mystery, but it was not yet matching with experiments. So then there was still a set of uncertainty. Although people thought that they are in the right direction, but they were not matching with experiments. So then perturbation theory was constructed first time, I think, in 1925. The first proper formalism of quantum mechanics came, and the experiments were there since 1900. So 25 years of unexplained results were explained after 1925. Within 1927 or 30, all this perturbation, all that we are learning was formulated, and people precisely predicted those numbers. And unless you predict those numbers, you precisely get those numbers from your theory. That's a nice theory, nice sounding theory, but nobody knows if it is correct or not. So that's why it's very important, this point, that this is the ultimate test of a theory, as I told you earlier, And later, I also told you that this eventually this was verified up to 16 place after decimal, as precise as it can get. Whatever the experimental best precision experiment you can do, the theory can predict it exactly, and that was the test of quantum mechanics. I mean, that is why this perturbation theory and all this, however difficult or however technically long it is, without that, it's a philosophy, right? It's not a theory. It's not a science theory, right? Okay, so that's why it's very important. So to learn how to do this, this is actually also the point where most people are, most students I know are feel like, okay, this is, I don't want to do this. Okay, but this, if you don't do this, then you rather shift to a philosophy department. Okay, because you have to now do, connect all the theory you have learned. You have to bring it to numbers, measurable numbers. Okay, until you do that, there is no point of doing that. So go through all the calculations that I'm telling you. All the calculations, do it yourself. Okay. So first class of problem is particle in a box with uneven float. Uneven float or some even float, but different. Even float, but different. So these are the two class of problems. So let me do it with some and here we will do two things, three kind of things. And this one we will do anharmonic oscillator. This one also we will just do, I'll not go to any of this, just yeah, uneven float. And here we'll do a variety of things. One is LS coupling, a partially relativistic effect, not the full Dirac equation. Then I'll do electric field effect. These discoveries were so profound, all of them won Nobel Prize separately. And maybe a bit of nearly free electron model. Okay. So this is basically the outline, and let's talk about first this uneven float problems. So as you can imagine that we did all these particle in a box, where Vx is basically 0 here, infinity here. So the simplest way to introduce a perturbation, so general ways are these. So you put a delta function. I'll discuss that a little bit, and or you put a bump. You can model the bump as you want. You can call it a semicircle, or you can call it a cosine function. So let's say you call this bump as like some cosine function. So b, where it is minus, so this is, let's say, minus 0 to a, and this is 0 to delta. So you can call it some cos 2 pi delta or 2 pi x y delta in this limit range, and everywhere else it is 0. So this is one example where you are modeling something, some imperfect modeling. It could be a semicircle or circle also. So I will give an assignment problem. I have an assignment problem on that. Try that. I will not solve it here. Or you could have, so another class of problem. This is one class. A local problem, a local something like which is at one point, at one small region. So another class is where you shift the floor upwards, right? Upward, downward, whichever way. Or what you can do, you can put a half barrier somewhere. Right? This is another class of problems. These are just, I'm narrating the problems that you find in books, and this is basically all the classes. One is this, another is this. So there is a difference between these two, important difference. So one of them preserves the symmetry, the parity symmetry of the Hamiltonian, another of them breaks that. This is also like that. This one breaks, this one preserves. Both of these preserves. If it is at the midpoint, if it is somewhere in one side, then it breaks. Okay? So they have important consequences. because eventually you have to calculate these kind of objects, right? Delta n at kth order h1 in t minus 1th order. So you can tell from here just by staring at this picture that which one of these are going to be 0 or non-zero, right? Because if this is breaking the parity and these two are of same parity, then those terms will go to 0. Right? So we'll see some more example of that in the harmonic oscillator context, but this requires some familiarity. Right? You spend some time with this problem, solving some of these cases, then you will stare at the problem and you know half the problem is done there, right? Just staring. You know which terms can go to 0. So this, again, this is important that you go through this. Okay, so there are two issues. One issue is you should be able to write your h as some h0 plus epsilon h1, but this term is small enough, and I told you what is the criteria of small enough, that these correction terms must be smaller than the energy gap, right? That is the criteria. So first criteria is this epsilon h1 must be small enough, which means this kind of terms h1 at 0th order, this is between n0 k0, they must be smaller than en0 equals 0. Okay. This is the small enough criteria which we discussed earlier, and that can be tuned by this epsilon. You can always choose your epsilon to be smaller, and you have to make sure your actual problem is within. If it is not, then you will start to see problems with level crossing. The second criteria is not criteria. This is an important point. Is symmetry. Mainly, since you are doing spatial problem, mainly it is parity symmetry. But when you do 3D problem, there are other kind of.
It's so small. Sir?
Yes.
So can you write bigger? It's not
Okay,
visible.
again the same problem.
The
Is
notation is
IT
not
guy is
visible.
there? Can you increase the? Okay, in this case, actually, I cannot do anything from my end. The resolution is fixed.
So
Okay,
actually
I will try to write bigger. Yeah.
actually more than okay. Actually the handwriting like very small, so only it's not visible.
Okay, I'll try to make it big. Okay. The second point is symmetry, and symmetry will help you to cut many terms to 0, basically. So basically, many corrections will go to 0. So these are the 2 points to consider. This is just a general strategy for solving this problem. And again, this will come through practice. Without practice, you will not know. For example, you are given a problem, at least for the exam or something. Let's say you are writing this competitive exam, where generally you have to solve a MCQ in 3 minutes, right? So in 3 minutes, you are not going to launch a full-scale calculation. So you have to stare at the problem and know what is happening there. Okay, this is very important. So this point I emphasized heavily in earlier batches because they solved the problem. Here I also just want to tell you that, and you will not understand this unless you are trying the problems yourself. You look at the problem and you try to construct at least half a solution in your head without actually solving the problem. So one such thing is symmetry. Another is boundary conditions. So these are the two general strategies, and there are several other strategies which you will learn as you will solve the problems. Okay, so let me just show the easiest one, which is this, that what will happen if you do that. So here the H0 is this, and your H1 is this, which raises the floor like that. Right? So you have to solve this for fast correction. So fast correction is En, so delta n fast correction. Fast correction is between 0th order. And that is basically very easy to calculate. So this is just this term. So let me call it V. So let's say the floor is raised by V. So this is just V. Just V. Okay. And it is trivial to see actually, because you know what you did. You just changed the floor. You just shifted the origin. So what will happen? This is not just It's for any state, right? So all the states will just shift by V, right? You know that even without solving the problem, and that is what just happened, right? It's a trivial kind of perturbation. So what you get, En correct, En0 plus V is actually an exact result also, but your first order perturbation is already giving that. And you can show that all higher orders will vanish. Higher order vanish. Because it's just a first order, just it's obvious because it's just shifting the energy. If you start getting V square V cube term, then that is not correct. Okay. So then let's look at another problem. That is also easy problem, so let me not write too much. Which is this one, the half problem. Okay. So what do you have to do? So calculate the first order correction. You have to calculate 2V0 by A, it is A, 0 to A, 0 to A by 2, this is just psi n, these two wave functions, but it is integrated from 0 to A by 2 because other half it is 0, right? So if you do this integral, you will get B0 by 2. Okay. So this is a little non-trivial result because you couldn't have guessed it. Because what you did, you raised the floor by V0, but in half of the problem. But what happens as a consequence, the first energy correction becomes V0 by 2, which is a little non-trivial to guess without calculation. Okay, so now let's do, what will you do if I want to calculate the first order correction in energy? I will just calculate this. I'm not showing the calculation, just writing down H1 from 0. So all these integrals you have to calculate, and can I see obviously which one of them is going to 0? No, I think they will all contribute because problem breaks the parity symmetry. So you will get all these integrals and just have to sum them. Okay. Okay, what else? Yeah, so another point I just wanted to mention that before I go to solve one problem more explicitly. So do this 4 and 5, try to do this 4 and 5. And you will see without doing, okay, first do the calculation, then you will understand that in one of these cases, certain terms will contribute and other cases those terms will not contribute. That is simply because you are calculating this between two wave functions, this perturbation, they have a parity which is either odd or even. Okay? So then if these two, if it is even, then even terms will contribute together, will vanish. And if it is odd, sorry, even terms will survive and odd terms will vanish. So whatever these two, if these two are odd parity terms, then they will vanish. Second one, you will see that if these two are opposite parity, so n and n opposite parity, they will contribute. And odd, same parity will contribute. So check this statement. Check this. It might be, I might have mixed between even and odd. Just check that. So do this calculation. You will see that lot of terms are going to zero. In these two cases. Okay. Similarly, another problem that you might be doing already, that if your H1 is periodic, 2 pi x by a. This is the Matthew equation, right? In solid state physics, you are learning Matthew equation, chronic penny model. Chronic penny you did now, right? By now, chronic penny model, tight binding. periodic lattice, right? So this Matthew equation, did you learn it there? Okay, so you may not have heard the term, but it is nothing but a differential equation, but the potential is sinusoidal. That's it, and that is what happened. That is the solid state physics told. There is a periodic potential. Of course, you don't take it sinusoidal always, but mathematically you take it this form. This is actually a very interesting problem because you can show that if there is a irrational number here, there is a irrational number alpha, let's say golden ratio. This is, then this problem has a drastic change in the solution. While what happens if there is irrational number? That is effectively like a disorder. So if you put it, let's say, let me put instead of a some p. So p is some smaller number than l. So then the problem, this problem is basically you have this particle in a box with something like this, right? The periodic potential with periodicity which is smaller than the full potential. If it is A, then it is just this, right? But instead you are doing this. So this is the floor. Now the floor is this. The floor is wiggly, but and sinusoidal. Right? So this is actually the problem of solid state physics, because what do you have? You have a wire or some 2D system or 1D system where the atoms are located periodically. Right? Of course, you don't write it like this. Instead, you model it like this. In solid state physics, what do? You do this. Right? It's a Coulomb potential, periodic Coulomb potential. You could have alternatively wrote it like this. Barrier. You can make it infinite if you like, or you can or you can make it barrier also if you want, which means you flip it. Right? So this is a model of that. So instead you are saying it is sinusoid. Right? So this is a sinusoidal flow. Now, if you want to study, so it turns out that then the solution will also have periodicity. That is the Bloch wave function. Plane wave multiplied by periodic wave function. The one more point to note that the problem you have solved probably in solid state physics, they don't have these boundaries, right? They are infinite. But in real world, everything has an end, right? There is a boundary. There is a wire cuts somewhere, right? So then you put a cut. That means you cut the wire. So then you can think of putting particle in a box and put a sinusoidal function. Now the problem comes. In most real world problem, this is not periodic. There is something going on. So let's say instead, add is like this. Right? Most real world problem is this, right? Impurities, disorders. Right? So then something very interesting happens. Then the periodicity or the plane wave structure of the solution is broken. So you see that the electrons get localized. So the wave function is exponentially localized. So in 1D you can show it will be always localized. 1D always localized. Always localized. In 3D you can show there is a transition. Transition means if there is a disorder. So this disorder is okay, let me draw this picture a little more better because this is extremely interesting. And it led to at least one Nobel Prize and hopefully more in future. So let me just do a 5-minute of detour of this problem. This has nothing to do with syllabus, but it's very interesting. This duster cleans very bad. No, it is also bad. All these written before are there. Okay, this is slightly better. Okay, so the problem is following. So let's say I want to model a solid. So how do I model a solid? So the main definition of solid is atoms are arranged periodically, right? That is the main definition of solid. There is actually also an issue about that, that you can show that definition of solid, liquid, and gas can be messed with, and it's all a matter of time scale. Like for example, well, periodic arrangement is one definition, but that is not the full definition. For example, one can say that it's the rigidity of the material, right? So then what do you call? The glass is also rigid, right? But the glass is not solid in the sense because it's not a periodic arrangement. It's an amorphous object. And they are actually moving. We cannot see that. Like there are these examples that if you go to these European churches which were made 1,000 years ago, you will see the glass is thicker at the bottom and thinner at the top because it flows. It flows under gravity. Right? So glass is actually a liquid, but the time scale of flow is so large that it's effectively a solid. So that's why there is a lot of ambiguities of how do you call something solid. It's a convenient definition which you use in some local use. Okay? So, but let's adopt the following definition. A solid is a periodic arrangement of atoms. That definition is effectively some. Let's just agree on that. Okay? So then you want to model it, right? And you saw this block wave function, Matthew function, and all that. So one definition of Matthew function is so instead of this, let's say I want to know what is the solution of Schrodinger equation when there is a periodic function. There is a periodic potential. So then you can say the Schrodinger equation is now d2 psi dx2 by 2m plus dx psi x, where this v is cos 2 x, some x. You can also put a if you want. That defines the periodicity. So this equation is called Matthew equation. This is a differential equation. I might have spelled it wrong, and this has a big literature. Okay? Now you want to model a scenario that there is a disorder. Disorder means like it is not exactly periodic, something is off. Right? It could be something is not there. There is an extra potential, or something has this, something like that. So one simple way to do that is something called quasi-periodic. So what happens when there is a disorder? Translation symmetry is broken. Right? 2 points are not equivalent. When you one more point to note that whenever you are thinking of a lattice, so this is a continuum model. This is not a lattice, right? If you discretize this, then it becomes lattice. So this is a continuum version of the lattice model. So whenever you are talking about lattice, there is already a symmetry is broken, right? Because this point is not same as this point. Right? So there is a symmetry only at a edge at this distance apart, certain distance apart. So this is called lattice translation symmetry. So in normally when you say translation symmetry, you say Tx is x, right? After translation by any delta amount, 2 points are equivalent. Yes, already symmetry is broken, but then a new kind of symmetry is there. That is called, yeah, but translation symmetry by amount A. No, a solid is not a symmetric object. The solid already breaks the space translation symmetry. So a solid has a special class of translation symmetry. So this is, so Tx plus A is x. So this is called lattice translation symmetry. This is also translation symmetry, but it's a more restricted version. And the whole difference you get, the physics of solid state, is basically because of that. Band structure, etc., all emerges from this just because of this change. It's solution of this equation, but with that extra constant. Okay, so actually you can also think of space. You can also think of a more restricted. So I don't know any of you heard about this field called lattice QCD. So lattice QCD is basically the problem of where they think the whole space-time is lattice. No, not just space-time, the 4 relativistic Minkowski space-time. And they solve that problem in that way. And they have a problem, of course, because as this A tends to 0, various kind of divergence appears and how to handle that divergence. Anyway, so let's go to the real problem. The real problem is solid is, And there is a simple way to think about that. Let us say if you imagine that and you look at in various directions, they are not equivalent. Right? But if you are inside a liquid, you look at various directions, or a gas at various directions, they are equivalent. Right? So a solid is a symmetry broken object already. And you can think of any phase transition as some sort of symmetry breaking. Right? So a solid to liquid is basically a translation from, it's a phase transition that takes you from a symmetric phase to a non-symmetric phase, right? And there are theories how to describe that thing, Landau theory and all that. Anyway, so let's not get into that, but let's come to this point that I try to make. So now I want to model this scenario that let us say this periodicity, the periodicity of this. So let me put a number here, a number called R, okay? So it is a rational number, P by Q. Then it is still a periodic function. Right? Not the same period as the lattice, may not be, because this number may not be repeating as this frequency of A or this periodicity, but it will repeat somehow. Right? P by Q, it is a rational number. But if this R is not a rational number, then even this symmetry is gone. Right? So this is the simplest way to study symmetry breaking physics. And there is at least one Fields Medal for solving this problem. This is called, this was given to Arthur Avila. And there is another person called Zhitovsky. She got some other prize for this. So this is called almost Matthew equation. So they solved it and show that, I mean, of course, it was known before. There was another two people called Aubrey and Andre. They wrote a paper in an obscure journal in Israel, which became very popular now, in some internal journal. They first showed that when you have a Schrodinger equation of this form, then there is a transition. So that transition comes as a function of V. When V is less than 2, all states are like this. When V is greater than 2, all states are exponential. And this is a critical point. Criticality, not only in the wave function. So again, you may not have heard the term criticality very seriously, but critical means, okay, it's very non-trivial to describe critical in a colloquial way, but you can think it's a phase transition point, and that is where length scales start to diverge. And length scale diverge means you can show these solutions have fractal structure. Have you heard about fractals? Any of you heard about fractals? Okay. So these kind of wave functions have multifractal structure. These wave function solutions, and not only that, this energy eigenvalues also have multifractal structure, which is very non-trivial. And this is a whole branch of mathematics to study this problem, which comes from this periodic potential problem in solid-state physics. Okay? So you are welcome to look into this. If you look at your term papers, Parvati did a term paper earlier on this, and she later did a research project also on. So you see the term papers, her term paper is there, so you can look at. Huh? R is some effective parameter which decides the periodicity of this function. So these functions, this periodicity need not be same as this lattice periodicity. Right? So this periodicity you can increase or decrease by R. So R, if R is P by Q, then after what interval this comes back to same phase? That is what R decides. Of course, this is a lattice version of this problem, is more relevant to solid state physics. But if you make it continuum by taking this A tends to 0, then it becomes continuum, right? Lattice continuum when you take A tends to 0. And this is actually an interesting question. All the lattice physics you are doing, whether the survives at A going to 0 limit or not. If it doesn't, then you know that's a property of this symmetry breaking, that 2 points are not equivalent because they are on a lattice. And other problem that I told you, this Anderson localization, this was the first time people realized that this problem is non-trivial. He won a Nobel Prize for this in 70s. So he showed that if it is 1D, if you have a little bit of impurity that breaks the transition symmetry, then all wave functions are localized 1D. And in 3D, he showed that if there is a finite amount of impurity, only they are localized. Finite means there has to be like, it's not exactly this. So finite means their potentials are drawn from a distribution which is from a range minus w to 0, and w is not equal to, w doesn't tends to 0 basically. W is some finite number. In this case, w tends to 0. That most non-trivial is 2D. In 2D, it turns out, even here, if w tends to 0, everything is localized. So that means there cannot be a perfect metal in 1D and 2D if there is even a little bit of disorder. Okay? So this is another class of insulator. As I told you, there are 3 classes of insulators. 3 classes of insulators that won Nobel Prize. There is a 4th class which is not yet, didn't yet win a Nobel Prize. This is one such class. The other 2 are Bloch and Mott. And the one which didn't win is topological insulator. Okay, there is a lot of physics into this, you can look it up. So the question is then, what if, like the problem I pose to you, that what you learned in solid state physics is this, that I have a cosine potential or some periodic potential, what happens to the solution? And the problem is basically infinite wire, because you have a 1D problem, right? 1D problem which has plane wave solution. Right? But if I cut that wire, cut means electron cannot go beyond this point. So now it's a particle in a box problem. So now what changes if I put this cosine potential? What happens if I change this periodicity? So this has a periodicity. Let's say it is P. Yeah, let's call it P. And this whole thing is A. So what is between P and A? And what if I put a irrational number? Now you might have to put it on a computer, or you can also do analytically, I think, this problem. So let's say 2 pi alpha x you put there. This alpha is irrational. Then what changes in this solution? And the simplest problem that you will find in textbook is this. So here just one cosine potential whose periodicity is same as the width of the wave. So play with this problem. You may not find it in a book, but just try this. Okay, so let's go to the harmonic oscillator. So there are actually infinite varieties of. So whole problem of band structure of electron and solid state physics is basically you want to deal with Schrodinger equation on a lattice with a periodic potential. That's it. And periodic potential means it is on a lattice, which means your d2x, d2. So for example, d psi dx. So that you write as psi x plus a minus psi x by a, right? So this is limit a goes to 0. Now instead of this, you have to just write it as, now your a is not going to 0 anymore. So that's where you get this. So then you write second derivative. Second derivative is, I think, x plus a. What is the second derivative discrete form? I just do this twice. Yeah, anyway, figure that out. It's just a finite difference form. Then you get the Schrodinger equation on a lattice when you discretize it, and then you get basically. Then you can think that when I cannot take the a tends to 0, then how the solutions will look like. That is what you are learning already. Okay. Okay. And in practice, actually, any problem is basically, when you put problems on a computer, then it is effectively some form of discretization, always. Okay, so let's do some anharmonic. Okay, so what do? My H naught is half m square plus half m square x square, and your H1 is x cube. First anharmonic term beyond any polynomial power. I am taking the smallest polynomial power, that is not x square. So H is now H0 plus H1 and you have to, so H naught has eigenstate which is n plus half H dot omega and psi n naught which are Hermite polynomials. So what is that? That is 1 by okay. So first correction will be simply this. And this term will be always 0 because of this cube, okay? Because this is a odd parity term. Okay? So first correction is always 0. So then what do you have to calculate? You have to calculate the second correction. Now to calculate the second correction, you need first order, the first corrected energy eigenstate. Right? So then you have to calculate the psi n1. So that means you have to evaluate these quantities. Of course, it will come with the denominator and all that. So how do you evaluate these matrix elements? It's very simple because they are in this, when you do it in this, as I told you earlier, if you try to do it using wave function, it's a notoriously difficult calculation. But if you use your algebraic form, then it is very easy. So notice that H1 is cube term, right? So cube means it will, first of all, it will not connect with any even pair. It will only connect with pairs which are like, which have this kind of a structure. X cube, yeah. So this H1 is proportional to x cube. That means it is a plus a dagger cube, right? So when you expect, there will be third power. So there will be terms like this: a cube, a dagger cube, a square, a dagger square, a square. Sorry, a dagger square a. Right? This kind of terms will be there. Right? So only connection you will get is this. So connection between n x cube n plus 3 0 of course. So I'm not writing the 0 but just assume this is 0 because then I have to be careful about writing n plus 3 0 and all that. So I'm not writing that. So n x cube n plus 1 n cube n minus 1 n x cube. So there will be this fourth kind of term you will get, and if you evaluate them, I'm not doing the algebra, just do it yourself. You will get, yeah, because these terms are lifting 1 and cutting 2, right? So n plus 1 will only come. Yeah. N plus 2, n plus 3 divided by 2 alpha cube. This will be 3 n plus 1 cube by 8 alpha cube. This will be 3 n cube by 8 alpha cube. There is also a very easy pattern of how to evaluate this. It looks big, but I want you to get your hands dirty. Otherwise, you will never learn this. Okay? I cannot do all the algebra. Just do these terms. It's very easy. Just algebraic expansion. Okay. So now I can evaluate the second order term once I know this. So second order correction. First order is 0. So I want to calculate the second order. So second order will be so there will be 4 terms. So 4 basically these 4 terms and nothing else. So they are n x cube. I am not writing the 0 here because it's cumbersome. n plus 3 mod square En minus En plus 3. Right, this is the first term. Then the second term is similarly n x cube n plus 1 mod square En minus En plus 1, and so on. There will be two more terms. One is this n minus 1, another is n minus 3. So after the dust settles, you will find En2. When you calculate all this, you understand, right? There will be two more terms. So when you calculate all these terms, you get 4h cube omega alpha cube n square plus n plus 11 by 2. So this is the final form. And similarly, you can also now calculate the wave function. So wave function also you calculate just the same token. You know this will be the processes. n not equal to n naught h1 n naught n0 minus n naught plus order epsilon square. So these terms you have already evaluated here. You just put it there. Yeah, there will be, this will be multiplied by I n0. Then you get all the corrections. You understood that, right? And when you do that, I also wrote down the solution. Let me just write down. What you get is this. The first term will be this. So you get minus 1/3 n plus 1 n plus 2 n plus 3 divided by 2 alpha psi 0. Why minus? Because this is en0 minus em0. em0 is higher than em. Right? That's why minus. Similarly, there will be three more terms which I am not writing. It's there in my note, and you can see that the only terms which will show up are basically psi n plus 3 with some factor psi n plus 1 plus psi n minus 1 plus psi n minus 3. And rest is all 0. There is no other term because it's x cube. Nothing else will contribute. So up to first order, only these are the terms. As I told you also pictorially, you have to figure out where that transition can happen. Only those terms will contribute. Right? And that you could have written it down without any calculation. You couldn't have written down these p factors without calculation. You could have written up to this much, this bracketed form without any calculation. Okay? Everybody is in the same page? Okay. This is complicated but easy. There is a diagrammatic way to do that also, but I will not do that now. Okay, I will tell you one more thing about quartic potential. There is something very interesting there, and I will not solve it, but I will just give you the tell you what happens there. So now let us say I want to solve this problem for x to the power 4. Okay, let me not wipe it right now. So if I do that, it turns out the solution looks like this. So notice that these are all numbers. These prefactors are nothing but numbers. For each level, they are just numbers. So book or paper, I think I wrote down that in my references, that does this calculation for up to 100 terms. So I'm just writing this. Russian scientists were famous for very high order perturbation theory calculation. They are very complicated often, but they are worth doing given you are looking for some physics. So So did you notice the problem in this series? Have you seen anywhere this kind of series? Huh? Yeah, so the problem is this term, it's supposed to be a series that is going to converge because epsilon tending to 0, it's going to converge. But this term that is coming because of the physics of the problem, this process amplitude term, this term is growing, right? So your epsilon have to be, you cannot choose whatever epsilon you choose. After a certain point, this term will start dominating. Is will have this convergence criteria, and then it will start diverging after a certain time. Okay. So then this kind of series are called asymptotic series. So people come 5 minutes late and leave 10 minutes early. Okay. Good. Okay. So you have seen this series somewhere, right? Have you? Stirling approximation in StatMech? Did you do Stirling approximation? N factorial. Right? So look it up. This is an asymptotic series. This is an example of asymptotic series. So these are everywhere, and these are one of the many reasons why mathematicians hate us. Okay? The point is, even with this series, you can match, you can get correct results. But the rule is, you cannot use it for a epsilon up to a order where it is diverging. Right? That's the only rule. So let's say you fix your value of epsilon. So that means this series is going, so let's say your epsilon is 0.000001, right? So maybe it is fine up to this, but at some point of time, this term will be so big, then you cannot use it there anymore, right? So then this is an invalid calculation. Then the whole promise of perturbation theory is broken. So this, whenever you have an asymptotic series, then for a given epsilon, you are constrained to use up to a certain order. You can choose a smaller epsilon if you want to go. And it turns out when you do this calculation, exactly, that's why I told you this 100th order perturbation theory is important. It is checked carefully that they match, their results match, which means even though it is mathematically problematic, they are good enough for us. Okay? So that same thing for Stirling approximation. No, nothing wrong. I'm not approximating with 0. I'm just saying I will not do perturbation theory after that, for that epsilon. No, those corrections are not usable. That is the point. And turns out, I know there is a degree of dissatisfaction, and that is an issue. And this kind of series you will see everywhere in physics, in Feynman diagrams, in Stirling approximation, everywhere. But the point is, there is a practical point that when this series is useful. So these series actually have radius of convergence is 0, actually, truly speaking. Because even in epsilon tends to 0, there is a certain point after which it will diverge, right? So the practical rule is you will go to this point and stop there, and that is the truncation. That is still the point your results are matching. Okay, so this is the point about this kind of problems. So very few things actually converge in physics. That is the point. Okay, so now I will talk about what state correction. So this is the energy correction. So the state correction is also easy to see. So let's say I want the ground state correction. So what I have to do, 0, 1. So ground state is 0. So minus, all the way I can go to the first excited state. So then you can obviously see that there will be only two terms, because your a plus a dagger is now power 4, right? So this acting on 0, if I expand it, there will be terms like, yeah, just check and you will get these three terms. No, I think I wrote something wrong, so I'll not write it here. I'll just write the answer. So one is, you will get event term. So 2 H10 2 H cut omega, because this is the energy gap. 2 minus 4 H10 4 H cut omega 4. So this, when you calculate this, you get minus 3/4 root 2 minus 1/16 4 factorial 4. Okay. And this term, you can also alternatively, you can get it like this. Okay. So this term is basically 4 times applying the creation operator. This is basically, you go 4 steps apart, 4 levels apart, right? So and so on. So then there are other higher order terms, of course. These order epsilon, then you have epsilon square order. Why it is order epsilon? Because this terms H1 has carrying in epsilon, which I have not written. Everywhere there is H. So this is basically the general solution. And at the end, once you are done with a given order, then you have to do this. That will give you the p-factor, right? That is the rule, that you normalize it after a certain level. Okay, clear to everyone so far? What? Okay, you have to practice this, otherwise you will not understand. Okay, now I want you to try one more problem. Okay, there is some 2-3 minutes still there. Yeah, just because many people left, that doesn't mean class has to be cut short. This is just long of simple formulas which we derived. There is nothing more in that. I mean, I cannot explain it to you any clearer because there is nothing to be more said than what I said already. Okay, so now do the following problem. So let me do a simpler version of this. Yeah, so let's do this. Let's take a 2D box. Okay. Now we know in 2D box there is this structure. The ground state is 0, 0. The first state is two-fold degenerate. Right? So now you are going to do something about that, degenerate perturbation theory. So let's put a perturbation somewhere, a delta function at point x0, y0. Okay? And we want to handle this. So delta function with some strength v0, let's say. So then I call it y is v0 L square delta x minus x0 y minus y. This L square is brought to scale this because when I integrate it, I want 1, right? I want v0. So that's why this L square is brought here. So this is the L length of the. Okay. So what will be the problem? So the first ground state, there is no problem. So ground state is non-degenerate. So you can do non-degenerate perturbation theory and calculate the correction. But the first excited state is problem. So let me, in my note, I think I named them 0, 1 or 1, 0. Anyway, let's just calculate the first excitation. So E111 is the first correction. So that is I110. Yeah, so I have named them somewhat differently. Yeah, I named them as 1, 1. 1, 1, 2, 1, 1. So 1, 1 is the ground state. So 110, H1, psi 110. So you can do this integral and you get 4v0 sin square pi x0 by L sin square pi y0 by L. Okay. So the degenerate part you can do very easily. Now you calculate the second order term, and so on. So one problem you will find here. No, there is no problem here. So now you at the end you can ask this question: what happens if your x naught is and y naught is at defined places? So you will find if your x naught and y naught is 0, x naught y naught is 0 0, then this term vanishes. There is no correction. Similarly, if your x naught, so now there are actually 9 such points. So they are basically these, or you can equivalently say this is 0 0, this is 0 L, this is this is L 0, this is 0 L, this is L L, this is by 2 L, this is L, this is 0 L by 2, this is L by 2 L, this, and this. So there are 9 points in this. Yeah, okay, figure it out. So there are 9 such points, but the first order correction is 0. Okay. So why they are 0? Then one can think a little more deeper into this. That has to do with the symmetry of the problem. Okay, so I am not getting into that. So, but it is just that. So then for those 9 points, if your delta function is located at one of these 9 points, you can go to the second order correction to see when is the first order correction coming. But the more important point is, what do you do with this part? What do you do with E12 and E21? This pair. This is a 2 by 2 subspace. It's a 2-dimensional subspace. So you have to solve the secular equation. You calculate this. So you have to calculate this matrix, solve this matrix. One, two, two, one, H1, 2, 1, 1, 2, H1, 2, 1, 2, 1. You have to solve this matrix equation. Something, right? This 2 by 2 matrix equation you have to solve. Do you understand what you have to do? So you have to evaluate these elements just like this. There will be 4 numbers. 4 number means some 4 small algebraic quantities. They are not numbered yet. I will tell you next class that how to actually do that. And diagonalizing that, this matrix will leave this degeneracy. Right? Now this is one more interesting point. You will get a function of x naught, y naught, and you will see this degeneracy is not lifted if they are located in one of these 9 points. Okay? So actually, you can easily see if it is located at the center, then it still has the same symmetry. Right? But we'll see that. We'll see those. But try to solve this part. Okay? So this is. I will give you one more problem if you are overwhelmed by this algebra. Try to do a simpler problem. So let us say I give you this matrix H naught, E1, E1, E2. We already did this problem, by the way, in this form, when your form is, when it was this. And I give you a perturbation. So try to solve this. This is exactly same as this, by the way. If you think it as a 3-level problem, or yeah, the levels. So this is like your E0. This is E1. This is E2. This is also E2. So you can call it also this. This is exactly a prototype of this problem. So if you can solve this, then you know what to do there. Okay. That's all. Except there is a difference in this problem, because this is actually an infinite dimensional problem. So there are many such things. In this problem, there are E2, 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 then E3, E3, like that. Now you are cutting this problem into smaller subspace and solving this in this example. So this is actually a practice. There is called this continuous unitary transformation. You can see this one of your seniors is doing a project on that How do you a problem into a smaller problem with consistency? This is a form of renormalization. This is called a renormalization, that where you are throwing away the higher energy space of the problem because you are interested about low energy physics of a certain bigger theory. Okay.
Sir,
Yes.
do you have class tomorrow?
Oh yeah, that's the point I have to decide. Okay, I will let you know. I have not decided yet.
Yeah, we have class from 9 to 10, so tomorrow.
Tomorrow you have a class from 9 to.
Ah, yes, sir.
What class is that?
Gravity.
You all have that class.
No, we have like,
Sorry, say that again.
I have a class from 9 to 10, so only us.
Only you have that?
I don't know, sir, whether
Okay,
anybody
what
else.
about you? What? What is that? Complex. These are all extra classes or regular classes? Oh, these are because of this three extra class thing or some other? Okay, it's for compensating. Okay, so I have not yet. Okay, so then let's not take any class to next class. So the only reason we had a provision of taking three extra class, and if I see I am going significantly slow, I am going to use that somewhere. And so far I am a bit slow, and but let's see how it goes. Okay? The syllabus will not end. I mean, in the maximum possible but it's okay. I mean, given the amount of gap you have, which means you are probably not following up, most of you. Okay, so I am not very enthusiastic about finishing the syllabus because there is not much point of piling up things on you when you are not following things. Let's see how it goes. It's better to go slow and understand everything. Where is the recording? Yeah. Better to